something right now.
No. I'm saying that it was like that is the input for the algorithm 1 and 2. I mean, yeah, basically.
Yeah, basically those are the inputs for algorithm 1 and 2. Yeah.
Yeah, but the important thing is you have to decide on a data structure. We talked about the data structure and everything. So that's you just cannot dump it inside a file or something like that.
Yeah, exactly.
No,
Exactly.
I'm saying, yeah, you understand that, no?
Yeah.
Okay.
So I was using network X. Could I store the 2000 long vectors in attributes for the?
Yeah, no. So the thing with the attributes is, C++, right? So don't store pointers in attributes. You can't do that basically.
Okay.
Right. You can only store scalar values and integers and things like that. Basically, you can only store scalar values. You can't store these vectors.
I see.
So you'll have to. We talked about this entire structure where we'll have a table, an external table indexed by the node numbers from network X, right?
Okay.
So if that's there in the GitHub.
Okay.
So then it will be basically an external table indexed by the node numbers in network X.
I see. Okay. So by the way, I'd like to ask a question about the way I split the network. So I took one of the 45 DNNs and then loaded the ONNX file in Python, and then got the weights and biases, and then used a network X graph where the weights and biases were attributes of nodes and edges, and then I did the splitting in the network X graph, and then got the new weights and biases from that network X graph, and then I built a DNN with those matrices. So that's fine, right?
That's fine. Yeah.
Okay, fine.
In fact, this last step you're saying where you're taking the network X and then converting it back to some format, right? Yeah. I think even that might not be necessary. The only thing that will help is that when you're doing the simulations, it'll make that faster, right?
Yeah.
So if you want to do that, you can do that as some sort of optimization step. Okay. But strictly speaking, everything in step 2, step 3, they only require the network X graph.
Okay.
Right. So even that step might not be necessary. But if you've done it, you've done it. So don't worry about it now. Yeah.
Fine.
Yeah.
If I want to convert it back to a DNN, how would I find the outputs of every neuron?
No, so we have converted from network X to a DNN. So when you say DNN, you're saying some PyTorch or TensorFlow. Right. So that is just, you can run that model, right?
Yeah.
Suppose if it's PyTorch, you just run the model on so you generate 2000 input vectors, right? So that will be a stack of 2000 vectors. The stack will be 5 wide, 2000 tall, right? So it's a 2000 by 5 matrix.
Okay.
Just run the model on that. So when you run the model on that, what you can do is the output vectors you will get, but for the intermediate vectors, you have to run it layer by layer.
Right.
So if, for example, if it's an nn.sequential model in PyTorch, instead of running the entire model, you run one layer, get the outputs, then run the second layer, get the outputs of that, third layer, and so on.
Okay. So I can define additional functions which give me the output for every layer.
Yeah, you can define additional functions in the module, but if it's an nn.sequential module, nn.sequential already just acts like a list of layers.
Yeah.
Right. So you can already just iterate over that and then run it layer by layer.
I see. Okay.
Right? Yeah. So when you convert it back, what do you have it in? When you say you have it as a DNN format, what do you have it in? Is it a TensorFlow model, PyTorch? nn.sequential?
Yeah.
nn.sequential, right? Yeah, then just run a for loop on the layers. If you iterate on nn.sequential, right? If you just run you can just say for layer in nn.sequential. That will give you layers from the beginning to the end. You can iterate on that, right? And then you just take the output, take the input vectors and run it on one layer, you get the output at one stage, run it on the second layer, get the output at another stage, and so on. The only thing you have to keep in track is that it will give you the layers in linear ReLU in that sort of a sequence. And remember, we only want the output of ReLU nodes. So we're not interested in the output of the linear layer, right?
Oh, yeah.
Yeah. So you only have to keep in mind that finally this list of vectors that you have, they shouldn't have the outputs of the linear layers, only they should have the output of the ReLU layers.
Okay.
That will be some codes, like some condition, like you will have to have inside where you check what kind of layer it is, and you don't keep it around if it's just a linear layer, right?
Okay.
Yeah. But you get the idea, right? It's
yeah.
Thanks. Shouldn't be too much complicated. Yeah.
Okay. So what else is there in this task? Okay, to generate. I
think those are the two things.
Okay, so these things have to be stored in a data structure,
right?
So that the downstream task can actually use them. Correct?
Right. Yeah.
For analysis, but make sure that this is parameterized with respect to your number of samples, number one. Okay, so they don't hardcode your number of samples, so that if you want to change the number of samples, you can do it. And you want some, what are some of the things that he has to monitor, okay, or print, or those things?
So I think for step one, there is nothing immediately. It's like step one is just preparing for other steps, right? I don't think there is anything that needs to be monitored directly for step one. And yeah, the point about, like, I think in general, just keep everything parametric. Like, so for example, even if you're hard coding samples to, like, you shouldn't be hard coding samples to something like 2000, right? You should at least keep a global variable somewhere that you can change in one place, right? So if we realize that 2000 is not good enough or it's too much, right, then it shouldn't be too complicated to change it later on down the line. Just keep that in mind when you're writing, right?
Right.
Yeah.
Okay, so just to be clear, I'll be collecting the outputs after every ReLU function.
Yes.
Okay, and what about the final layer? There I'm not applying ReLU, so I'll just
the normal outputs there.
Fine.
Right, and actually, this is an important point. Don't consider the final. Then this is for everyone. Like, you don't consider the final layer neurons for merging.
Yeah. Okay.
Okay, so when you, even later on down the line, when you select one of these nodes, calculate S score and select this node as an output of a merge group, and then decide whether create the merge group and decide whether you want to merge it or not. Don't take the final output layer neurons if they don't have a ReLU. So the idea is that we're only going to merge neurons which have ReLU on it, right? So generate the data still for it. I think that is if we decide we have to generate like the data later on, then it's good to have the data generated already, right? But just making sure that, like, you guys don't end up merging the output layer neurons, because then they are just linear, right? If they're already linear, and what we're doing when we're merging is looking for a linear bound, it's like this merge process will not give us any benefit, first of all. And secondly, what we'll end up getting always when we do this sort of analysis of the components is that we'll get the entire previous layer as the inputs. Right? So I don't know if this point is coming across very well or not, but I think I want to make this point. So I'll share screen really quick. Yeah, so this is a good question regarding the final layer neurons, right? So suppose your network looks like this. You have some inputs, then you have an intermediate layer, and all of these have ReLU on it, right? So the inputs don't have ReLU. So let's use a different color for that. Some inputs, intermediate layer. And then we have again some outputs which don't have ReLU, right? Let's have another intermediate layer just to, yeah. So now, if you look at this neuron, right? Since this doesn't have a intermediate layer, the output of this neuron is already a exact linear function of the output of this, this, and this. Correct? Does that make sense?
Yeah.
Yeah. So if this is already an exact linear function of this, so remember what we were doing is we were trying to get the best fit linear function, right? Get best fit linear. And that is going to give us an S score. And then using this best fit linear function, we also try to get coefficients, right? And then from those coefficients, we get merge group. So this entire process, this depends on this best fit linear function, right? So if the best fit linear function is actually just the linear layer itself, so in this case, it's just going to be the linear layer itself, right? And it's going to be an exact. So what you'll end up happening is you'll get a best fit linear function, which is exactly the linear layer itself. The S score will turn out to be 0. So everything at this point is telling you that, okay, look, this is a very good merge candidate. But then when you start looking at the coefficients of all of these neurons will be 0, right? So when the coefficients of all of these neurons are 0, then what you end up getting is, okay, the input to the merge group are going to be just these, right? And at that point, how do you even construct a merge group, right? Because then the only thing inside your merge group is just this neuron, and that is like you already have a linear node there, right? So there is no point in trying to merge the output layer neurons if they don't have ReLU. So then what you should do is in the later stages when we're looking for output nodes of the merge groups, ignore these. So ignore these, right? When you're looking for output nodes of the merge groups, just ignore these. Similarly, when you're trying to merge something, ignore this. Your merge groups will never look like, so the merge groups should essentially never look something like this, right? We're only going to look for merge groups that look something like this, or, this, right? So does that make sense with everyone? Is the reason why I'm saying that you shouldn't look at these?
Yeah,
it's clear, right? Yeah. So
both for the purpose of these initial experiments, histograms, as well as later on for the real thing that where you construct the merged group, only look at those neurons which are outputs of ReLU nodes.
Which have ReLU in them, right?
So that then it'll regress as far back to possibly all the way to the inputs for the input neurons feeding into that merged group, into that output group.
Yeah, that is basically the point. So just to make sure, like if these nodes were actually had ReLU on them instead of being not having ReLU on them, then you would have considered them. So if the output layer does have a ReLU, then you consider them. But if the output layer doesn't have a ReLU, then you don't, right? So is this idea okay with everyone?
Yeah. So we take for the output, we should take, any of the, maybe pre-final layer, or we can actually take with a layer before that also, theoretically.
So if you want, you can consider the layer, like you can sort of, what you're saying is this is kind of like chopping off the network at this point, right?
Right.
Yeah, you can do that. The only complication is that then what about the properties, right? So you'll have to transform the properties again. I mean, if you think that will be easier for you to code up, or it'll be easier for you to organize things in that way, you're free to do it that way. Right. But or you can also write a condition where you ignore these nodes while merging, whichever you prefer. But if you want to chop off the network at this point and then convert the properties to an equivalent form, you can do that as well.
Okay. So right. So suppose we take one of the nodes of pre-final layers as output. So do we keep the output layers also, right? For the vectors, while calculating the scores and all.
I didn't understand your question. What do you mean by keep the output layers while calculating the scores? So suppose you're calculating the score of this neuron. If you're calculating the score of this particular neuron, right?
Yeah.
So then the only thing that will ever factor in this calculation of the score is are neurons coming in layers before this neuron, right?
Right. Yeah. That's
So yeah, it doesn't matter whether you have kept it or chopped it off or whether you're ignoring it or not, like the other layers, right? The
right.
output layers. Yeah.
Understood.
Okay, so is this clear with everyone? Any questions? Do you want me to, because then I'll maybe stop sharing.
No. Keep it. Okay. Let's say until everything. So before we move to the next, task, given this clarification and so on, and whatever the status of your current thing, because for getting some initial experiments, which is one of the requirements that we have, this is very crucial, Dhruv, and therefore completing your task. So you think that you'll be able to get it done by the end of today? I mean,
yeah, I think I'll be able to do it by today evening.
Okay.
There's only just one uncertainty, and that is whether I have constructed the correct DNN. So
what do you mean? In terms of classification of the node attributes. Why?
Yeah. So I've obtained the modified weights and biases. I'm pretty sure that I've done everything correctly up till that point. My uncertainty is where I'm incorporating those modified weights and biases into my new neural network.
So your uncertainty, so there are a few steps, right? So
yeah,
so you have a DNN.
Yeah.
Then you go from that to an NX model, right?
Yeah.
Then you do the split.
Yeah.
So you've got NX prime now, let's say, and then you are going back to a DNN prime, right?
Yeah. The final step is where
this is where, yeah.
So I created a PyTorch model on. I created a PyTorch model, and then I assign those weight and bias matrices to each of the linear layers. So I'm just worried about the dimensions and all.
So if you're worried about dimensions, is something that you'll get a very clear error message for, right? If once you've assembled a model and if the dimensions don't match of the layers, right?
I'll get some errors.
Which is why when you do the simulation, you'll get it, right? And of course, I mean, you're worried about this layer, but if the dimensions are wrong, that might be due to any layer previous to it, right? As well. Any step, sorry, not layer.
Yeah. I'm just getting some inconsistent outputs, but yeah, let's see.
So I'd suggest if you're worried and if you want something, you can do one sort of unit test, which is that, see, and this will sort of tie into generating the simulation data as well. See, when you're going to be generating the simulation data, what you'll have at the end is you'll have a bunch of, you'll have this huge, bunch of input vectors, right?
Right.
So what you can do is you can feed it to this DNN and see what the final layered output, the outputs are. So the output at this layer. So you will get Y1, YN, right?
Yeah, I should get the same thing for.
From this as well. Because remember this.
So I got the same outputs, but I'm not sure if I converted the. Okay, how should I?
So when you say, but you have not already.
The other thing that you can do is, I don't know what DNN that you used for your test. You use something small, like in the paper. Okay, what you have in the paper, that also gives the NX and NX prime and so on. So you could actually compare them as well.
Yeah, you can take the DNN in the paper. You can take the DNN in the paper, maybe add one more layer to make it a little bit more complicated, right?
Okay.
So
Okay.
that like if you're getting some weird results, trying with a small network is going to pretty much be the only thing you can do, right?
Okay.
But
Okay,
anyway,
just one
like,
thing.
what is it you're facing?
Okay, so like I'm getting all my outputs and
Mm-hmm.
even the outputs of the two DNNs match.
Mm-hmm.
Uh, one of the weird things is when I remove one layer from my DNN, from my new DNN,
Mm-hmm.
the dimensions of my output become 50, whereas it should be 5.
That is fine. No, if you're removing the output layer, see
No.
the
I'm removing a hidden layer.
you okay.
Yeah, so
So I'll tell you something about PyTorch, right? So what you should do to debug that is like you'll be writing this layer by layer code, right?
right.
If you want to debug the dimensions, just print out the dimensions of the vectors in each layer that you're calculating. Often what happens with PyTorch has this feature called broadcasting, you know, right?
Okay.
So basically the idea with broadcasting is that if you have a operation, like let's say that you have a matrix M and you do star with a vector V, right?
Mm-hmm.
So remember that like this star doesn't mean matrix multiplication, it means scalar multiplication, right?
Okay.
But then what does it mean to multiply a matrix with a vector V? So what they'll do is they'll broadcast it. So the matrix can be considered as a stack of vectors, right?
Mm-hmm.
So you broadcast the operation into the output of this is going to be a stack where the output of this. So if you consider this as R1 to RK, right?
Mm-hmm.
The output of this is going to be R1 star. These are all vectors. R1 vector star V vector, RK vector star V vector. And then each one of these is also going to be broadcast again and so on, right?
Okay.
So there are semantics of this sort in PyTorch and NumPy. You can go ahead and read about broadcasting a little bit, but that often leads to sort of weird dimensions. But yeah, print out the dimensions and that'll make it clear.
Fine.
Yeah.
So that's all. I think I can get the simulation results right or wrong by today evening.
No, but like if you're suspecting that it's wrong, then there is not much use in getting simulation results, right? Like
right.
Yeah, do make sure that there are no bugs, at least as far as you can tell, of course. Like I mean.
Okay.
Yeah.
And one thing, the original DNN was in ONNX format. I would like to directly convert it into a usable DNN format. So, how do I do that?
Directly, but so when you say usable, what do you mean?
I wanted to convert it into a PyTorch model.
So you can. So there is a library called ONNX. Install this library.
So I can do it with ONNX only.
Yeah, you can do it with ONNX.
I was using that library. So
I think you can do it. Let me just check the docs, but with ONNX only you should be able to do it.
Okay.
But I'll check it. Just a sec. I can check it.
Okay. If I could do that, then that would be really good.
So how are you doing it right now? Are you writing some sort of ONNX parser?
No, so I import I just use the ONNX library to load the ONNX file, and then I obtained the weight and bias matrices using some function from that library.
Right. So you're basically writing some sort of a parser for ONNX in some sense. Then.
I see.
Yeah. So you can do that, but I think with this also, like with ONNX, you should be able to get a PyTorch model. So
okay.
Where do you use the
actually,
library?
there is a library called ONNX to PyTorch. Actually,
there is a library called ONNX to PyTorch.
Yeah, that kind of gives that you can use the model.name parameters. That kind of gives you all the things.
The one you were talking about.
So what is the name of the library?
Okay.
ONNX to PyTorch.
This. Okay.
Yeah.
Nice. Yeah, it's on PyP, so you can just, yeah.
Fine. Then it will be easier to verify my outputs.
Hey, just a side observation. Soham, you already knew this. Shouldn't you know,
No,
you
no,
guys
I-
should be
I
talking
didn't
to
ask
each
on the
other
group.
a little
I
bit
told
more,
him.
isn't it?
Yeah, I was.
No. Just an observation. I don't want any, you don't have to answer. Okay, so you should be talking to each other more, helping each other.
Yeah, I didn't ask him the question.
Okay.
Okay.
Yeah,
fine.
but anyway, I think you should be able to use it. But if you're worried about it, or if you suspect the code you have written, just replace it with this, because this is already very succinct, and it's probably has better chances of being completely correct than what you have
Right.
written. I have found, like, I wrote a parser for ONNX, not to PyTorch, for some other format, and it was horrible. So yeah.
Okay.
But I think even this one is there, so you can do this also, torch.onx.
Okay.
Yeah.
Fine.
So anyway, so that is
Yeah, and just one final thing.
right.
How should my format of the outputs of every neurons be?
Right.
What?
So
Yeah.
you remember we had discussed this. There was the GitHub repo where I had stated how it should be, right? Let me just bring
okay.
that up actually. So right now it just as an M, like README, there's nothing else, because we had thought that we'll put out some common code, but then you guys got extra time. So, but yeah, you guys, all of you have access to this. So this is the idea, right? This much you already have. You already have a network X model where edges stored weights and like nodes stored the biases and edges stored the weights, right?
Yeah.
Yeah. So now what you're going to have is you're going to have external data structures, which basically are like tables indexed by neuron indexes, right? So what that means is that you can just think of it as a dict where the keys are of neuron index. Each key is a neuron index, right?
Okay.
And when I say neuron index, you remember that NX will give you an index for each node in the network, right?
Yeah.
So that is your neuron index. And then the values can be various number of things, right? So for example, when you're splitting the type of the node with like some data of this sort of, this can be one sort of data structure, right? Whether it's unmerged or merged, right?
Okay.
By type of node, I mean increasing, decreasing, positive, negative, right? Secondly,
so basically, I
right.
create a Python dictionary.
Yeah.
Oh, fine.
Okay. I'm sorry. I'm completely missed a part of this thing. You'll also have to do the interval propagation as a part of step 1.
I see. Okay.
Yeah. I'm sorry about this. I don't know. I completely missed saying that.
Okay. So, does that come at the end?
Yeah, that can come at the end.
That can come at the end. Yeah.
So
you don't need to do interval propagation right now. You just get the, like, by tonight, that doesn't change. By tonight, just try to get the simulation
output.
Yeah, because the initial experiments don't require interval propagation.
Okay. And okay, if that like, if I was to do interval propagation, what would I have to do there?
So you remember we talked about when we were discussing deep poly, even before we discussed deep poly, there was this interval domain which we propagated through the network, right?
Right.
That's what you have to do. That's exactly what you have to do.
Okay, just like in some more details.
Okay, sure.
So, like, what interval do I start out with?
So the starting intervals for both interval propagation and starting intervals, this should come from property always, right?
Okay.
Whatever the input constraints are. Yeah.
Right. So this is basically just the input constraints inside the property.
Fine.
So for example, if your constraint says that, so let's say that theta is between, let's say, minus 0.2 and then 0.2, right? So then this is starting interval for you. Same thing when you're doing the sampling for the simulation as well. So you're going to use this same starting interval to sample, and you're going to also use the same starting interval for interval propagation.
Right. Fine.
Okay. So starting intervals come from the property. then what you have is, see, at any point you have, like, let's say you've done the interval propagation up to the previous layer, you now want to do it for the next layer, right? So you have a situation where this is the node in your next layer, you've got a bunch of nodes in your previous layer, right? And you know intervals for this. So you know L1 is greater than the value of this node, and this is again less than U1. So you have L2, U2, right? L3, U3, and L4, U4. So now what you know is this will connect up to,
right. Okay.
Right,
So
via some weights and biases. So this node's output, if we call this Y is going to be, and let's call this X1, X2, X3, X4. Y is going to be some W1, X1 plus W2, X2 up till W.
So it's going to be an union of intervals.
You don't even have to take it as a union of intervals. It's not even going to be union intervals. Like you can, like this is a function, right? This is in general a function from X1 to X4 to Y, right?
Right.
Just figure out what the upper bound and lower bound of Y should be in terms of the upper bound and lower bound of X1, X2, X4.
Fine.
Right. So it will be basically this. If this is the function plus some bias B, right? Then the interval is just going to be W1, L1, W4, L4 plus B. That's the lower bound, and the upper bound is W1, U1, W4, U4 plus B, right? It'll just be something like this. You get the idea, right?
Right.
You're just saying that, okay, if the inputs to this is a linear function, right? So if the inputs are less than this, then the final linear function is also going to be less than this, right? Similarly, if the outputs are less than this, then the final linear function is also going to be less than this.
Yeah.
Does it make sense?
Yeah.
And then similarly for ReLU also, what do you know? So for ReLU, you have, say, Y is equal to ReLU of X.
Yeah, I'll just take the part which is above.
Yeah, that's it, right? So if you know that, L is less than equal to X is less than equal to U, then what do we know? You know that Y is going to be what? It's going to be basically, if L is less than 0, then it becomes 0. Otherwise, L remains L. Similarly, if U is less than 0, then it becomes 0. Otherwise, U remains U, right?
Yeah.
So it's just this.
I'll have to give the outputs at every node in this case as well. Like the intervals I'm getting for every node.
Yes. Intervals for every node you need. Yeah.
Okay.
Yeah.
That should be easy.
Yeah. Interval propagation is not like, it's very easy.
Fine.
Yeah. And I think I mean, if you want, I feel that I had sort of talked about this in some detail during the deep poly lecture. So if you want, you can go back and look at the deep poly lectures a little bit. The beginning part of this will discuss this.
I think so.
Sure.
Yeah.
I
think I have titled the lectures fairly descriptively.
Yeah.
The YouTube video list. Yeah?
Right. Okay. Otherwise, you can just, watch like couple. You'll remember what happened before and after, right? So you'll be able to find it, hopefully.
Right.
Even if you don't remember of course, how you can't remember the exact date when it happened. So, okay, any other questions about step 1?
No, I think this clarifies all the doubts that I have.
Yeah, sure. So if you have any questions anytime, just feel free to call, write.
Oh, okay, sure.
Yeah.
Thanks.
Yeah. I mean, even if I might not be able to answer anything immediately.
You will have you will generate the things to pass it on to Soham, correct? Yeah.
Yeah.
Yeah. Okay, good.
So now, what about the other people? How do you guys do?
Let's go in that order. So number 2, Soham, if you could, part 2.
Yeah.
Get your proposal. Okay.
Yeah. Once I get this result, it will not take much time. I mean, I have seen that. I mean, I was trying some of without that split network. It's just running the least squares and then it's very simple.
Oh, okay.
I mean, I would be it should not take much time. I'm just concerned about this.
Nonetheless, tell me if you have any doubts. I mean, what you, yeah. So just
this threshold coefficient, selecting those threshold coefficients, that just, I mean, I need to see the results, what kind of values we are getting with using this simulation.
Right. So you're saying what kind of values are we getting for S, right?
Yeah.
And you're saying that based on that, how do we decide what to put TS to be, TS and TC to be, right?
Yeah, right.
Yeah. See, this is a very pertinent and good question. This question of what should TS and TC be, right? And the idea is, see, this entire code currently is parameterized by TS and TC, right? But what does TS and TC control? TS will control the number of merge groups. Does that make sense? Because you'll keep merging until you don't have anything less than TS score,
exactly.
right?
Yeah,
so this is number of merge groups.
Right.
Then TC controls the size of each merge group, right? Because if TC is very small, then nothing will be considered as like being close to 0. So then all of those things appear, most things appear as inputs, and your merge group will be small, right? Whereas if TC is large, then again the merge group will be large, right? So together these control the number of merge groups and the size of each merge group. So does that make sense?
Right. Yeah.
So together they'll control the level of approximation you have. So this will give you how much approximation you have. Now, what we want to do ideally is we want to find the largest amount of approximation we can get away with, right?
Right.
Because we want to be able to do the proof, but you also don't want it to be like not approximate enough, because that will take too much time, right?
Okay.
So that's the idea. Like on the one end of the spectrum, if it's very approximate, it will be very quick, but then you don't have a proof, right? On the other end, it will be very exact. Like you can pass the existing network as is, but that will take a lot of time, right?
Yeah.
So that is the idea. So now we have to, so this spectrum. So basically you have this sort of a spectrum, right? Over here, we have no proof because this is too approximate. And here TX and TC will be too large, right? And similarly, here TS and TC can be too small and takes too long because it is too exact. Somewhere there is the largest TS and TC we can get away with, right? Like somewhere there is a point beyond which we can't do a proof. Like somewhere there is a point beyond which we can't do a proof. We choose TS and TC values here, we can't do a proof, right? So what we're looking for is this largest possible TS and TC value which gives us a proof, right? Now, how do you actually find this? There is no, like, at least I don't have any smart way as of now. What you'll do is you'll just try a large enough TC value. If it doesn't give you a proof, you try something smaller. If it doesn't give you a proof, you try something smaller, and so on until you hit this value. Does that make sense?
Right. So, what do you mean by this doesn't give you a proof, as in this context?
So in this context, you'll do all the merging when you have the entire code done, right?
Right.
You do all the merging, you pass it to Reluplex. The Reluplex, if it doesn't give you a proof, the Reluplex will do one of two things, right? So
it will pass or
so it pass on the your network, a formula representing the network, as well as the property.
Yes, to Reluplex.
The negation of the property, actually.
Yeah.
To Reluplex. And Reluplex will say,
it'll either say SAT or unsat.
Unsat, which means that it's verified.
Doesn't pass.
It's success. If it says SAT, then you have, that's the case when it is you're not sure.
Yeah. So I'll basically maybe elaborate this point. So you have a DNN, and then now what you know is you have abstracted it. This is the entire code that you've written, right? So you're creating an abstract DNN. So this is all of the code. So now you have a DNN n prime, let's say, right? Now what you know is the output of n prime is always greater than or equal to output of n, right? On all inputs. This is the property of your abstraction, correct? Is it fine so far?
Yeah.
Yeah. So now when you pass this, you pass this to reluplex. You pass this, and you also, also have the property. And remember, the property is what? The property is going to be some upper bound on the output, right? It'll have input properties, but you also have an upper bound on the output, right? So you negate that, and you get some, and you pass it to reluplex. So that will basically look like you combine these two things, pass to reluplex. So now what you're asking reluplex here is there an input? So you're asking here, does there exist an X? So let's say the upper bound is B, so that n prime of X is less than B. That is what you're asking at reluplex over here, right?
Right. Yeah.
Right. So this is what I mean when you say negate the property. You add the constraint that n prime of X should be less than B, and you also have you've also encoded the entire network, right? So when I say n prime of X, you basically have the network encoded into reluplex as well, right?
Right.
So when you're asking reluplex this, then reluplex can tell you one of two things. It says no. That means what? That this question or this set of constraints is unsatisfiable, right? You cannot satisfy the fact that, okay, maybe I should write it like this. You cannot satisfy the fact that y should be less than b and y is equal to n prime of x, right?
Yeah.
These two can't be true at the same time. So if it unsatisfiable, then we know that always what we know is n prime of x is greater than or equal to b, right?
Yeah. Right.
And we know that, look, this n, okay, wait, so this is the, I don't know what, okay, I think I've just confused myself. Just give me 1 second.
That's correct.
Yeah.
Prime is greater than n.
So, and n prime is also greater than or equal to b. So, but then how do you conclude from that n will be greater than or equal to b? Because n is...
You have to be careful, okay? It always gives something. So your...
I don't know why I'm confusing myself.
No, your property will be saying that y is less than or equal to some constant.
Oh, yeah. So I think I've...
So the negation
yeah.
greater than, okay?
Right. Sorry.
So
I have missed this.
Yeah. So your property...
So I should write this very clearly. So the property is for all x, nx should be... So this is the property. I'll write it up there. T is for all x. And you'll have some input constraints. Nx should be less than or equal to b, right? So when you negate it, you should basically give reluplex something like, does there exist an x? Let's say that this input constraint is phi of x, right? Such that phi of x is true and y is equal to n prime of x and y is greater than b. So that is what you're asking reluplex. Sorry for messing this up and confusing you potentially. Is this clear so far? Yeah. So if reluplex gives you unsat, that is, there is no such x. That means what? That means you know that for all x, phi of x, for all x as phi of x is true. You know that n prime of x is going to be less than or equal to b, right? From that, you can now tell, because you know that your abstraction is such that of this kind, right? You can now say that nx is going to be less than or equal to b, right? Is this clear?
Yeah.
But if RealPlex tells you SAT, now what you have is you have an X, right? RealPlex has given you an X such that phi of X holds and n prime of X is actually greater than B, right? But this does not imply that for this same X, phi of X, for the same of nx will be greater than B. We don't know this, right? So you see here also two things. So it's clear that we don't know this, right? Because if n prime x is greater than B, all we know is that nx is actually it's going to be less than n prime of x, right? So we can't tell whether it's going to be greater than B or not, right?
Right.
So now here also there can be two situations. So here what you do is now you try, so you calculate nx. Remember that this point x is just some vector that you've gotten out of Marabou, right? It's just some concrete set of values. So you calculate nx and check if nx is greater than B. So if you get yes here, then you have found a counterexample, right? Does it make sense?
Yeah.
Right? So then you can output this. So you return false, right? Because the property doesn't hold. But if you do get no here, then you don't know anything. You haven't been able to conclude anything, right? Because just because nx is less than B, it doesn't mean that actually, like, you're seeing that nx is less than B. So you can't say that the property doesn't hold, right? If somebody asks you why are you saying the property doesn't hold, you don't have any good reason, right? You don't have a proof that the property doesn't hold. And similarly, you also don't have a proof that the property actually holds, right?
Yeah.
So now the proof fails.
Well, yeah, the proof is
Incomplete. This is inconclusive.
Inconclusive. Yeah, success, failure, inconclusive. Yeah.
Yeah.
So
Yeah.
the three.
So yeah, so this is like return true, return false, inconclusive. Or this can also be, success. But basically these are the ideas. So
yeah. So anyway, so you have to these things are recapping. Okay. So
yeah, I think these things were covered in some detail.
But I mean, related back to your TS and TC. So it is here that you refine your TS and TC. Okay.
Right.
It's in the inconclusive case. Yeah.
Yeah. So then sort of the large scale loop is going to be start with some TS and TC. Right. And then do the entire proof, try the proof. So when I say try the proof, you do this entire thing, right? If it succeeds, if you get true or false, so you try the proof. And again, this try proof thing is the entire code that you have written. So if it returns true or if it returns false, then you can just output that, right? But if it returns inconclusive, then what you want to do is you want to go back and try the proof again, right? So you want to just do something like this. So you want to try a smaller TSTC. Okay. Does this now make sense to everyone?
Yeah, more or less.
Yeah. So try proof is that one step is what you're actually implementing through the various algorithms that Diganta has documented in his write-up. Okay.
Yeah, this is the entire thing. The entire implementation is just going to be tried.
If the initial experiments are just a step towards that thing. So your initial experiments is just to shed some light on how good a merged group that you may get and so on and so forth. Okay. So, and then it can also serve in your case to do the initial experiments because it will be a test that your implementation is correct. Okay, so I would still encourage you to go through producing the results of the initial experiments. Although the other group has already produced the initial experiments, but still, it'd be useful for you to do that while you are going ahead with implementing their algorithms towards completing the strike-proof green highlighted thing that you have. Yeah, go ahead. Yes.
Yeah, that's the sort of. So I mean, the big picture idea of what TS and TC should be is clear, everyone. I mean, what is the purpose of TS and TCs?
Yeah, it's clear.
It's not clear.
No, it's clear.
Okay.
Yeah. So your algorithm 2 will, part 2 contains, finding the best possible output neuron. Generating scores for all the neurons. Okay.
So I want to ask you, is the generating scores code done? Because you said that, you don't need a split network to do this. You just need a network to be able to do this, right? Like you don't need the fact that the network has to have this like increment property to generate the scores, right?
Yeah, but of course it needs some vector of values.
Right.
Each
right. That is necessary.
Yeah, assuming that you have that network. I'm sorry.
Right. So so there is no way you can actually like write the code as of now before that vector of values is.
No.
Exactly.
Why? You can assume something and generate some score, no?
Yeah. You can at least have the code.
You can write the code, assuming that the data structure stores that data in a particular format.
So basically what Sir is saying that assume, so we talked about how Dhrubajyoti was supposed to generate these simulation results at each point, right? That is what you're going to use Soham to generate your scores, right?
Yeah.
So just assume that like you have that and write the code, and while writing, like testing the code, just test it with random vectors or something like that, just to check that the code just runs and there are no obvious bugs, right? Because because then you will be basically in a position where as soon as Dhruv is done, you can immediately take it and run and get the scores, and the experiment will be done, right?
Yeah, right.
Right. So then basically by tomorrow sometime we should hopefully we can get some results for the experiments, initial experiments, right? Is that
Yeah. It will not take much time to write.
What I'm saying is you could do some parallel processing even while you are doing it. If you have not already done it, you might as well start doing it, is what we're trying to impress upon you.
Yeah, sure.
Yeah, I think your second bullet in part 2, that is, of course, it's another loop, okay, which is use the previous part to choose the best possible output neuron. Once you get scores for all of the thing, and that is just a matter of iterating through the neurons to do it, and generating the corresponding input neurons. Okay, now that's also part of algorithm 2, isn't it, Diganta?
Yeah. So I think it is also. It's a part of step 2. I don't remember.
It is part of step 2, but I think corresponding input neurons getting it is algorithm 3. I think.
Yeah. So just a sec. I'll just open up the file.
Algorithm 3 is getting the merge group.
Yeah, that will require you to choose the input neurons.
It takes the
input neurons is part of algorithm 2 probably. Okay.
So.
Yeah, you could display it.
I'm opening it. Right. Okay, this is not the file that I'm.
No, I have it.
No, I think I don't have it. I'll open it up.
You want me to send it?
No, I can get it from Moodle itself, right? Right now, things have become sort of spread between this laptop and another laptop. So I'm sorry. directly very organized. Yeah. Yeah. Is this visible?
Yeah.
Yeah.
This is certainly, yes.
Yeah.
Yeah.
So algorithm 1 is going to just be
Least square application.
right, the least square one. And you have to just repeat algorithm 1 to get the scores. That's all.
Yeah.
Right. Then finding the best output neuron is basically just iterating on algorithm 1. There's nothing much here at all. Right. Is that okay?
Yeah, but that's where there's some subtleties that that come. Maybe you want to okay, so choosing the neurons will require you to pay attention to corner case 1 and 2.
Yes. So
I want to make sure that Soham, since you're implementing that, I guess you're implementing 2 and 3, correct?
Yeah, I mean step 2, whatever.
Yeah, no.
Correct.
Step 2 is enough for generating the initial experiments, but step 3,
no, so I mean, even when you're implementing step 2, just keep these two corner cases in mind. See, when you'll basically be choosing the best neuron and so on, and then finally when you find the merge group, you're going to take in the list of input neurons, right? And if you look at the list of input neurons, it is going to come from this algorithm 1 in itself, right? So here I haven't written it in the code, but if you have a situation where, for example, you're getting that all the coefficients are greater than TC, basically, if you get, these are the two corner cases, right? If you get all the neurons in your network are input neurons and no neurons in your network are input neurons, right? So in those two corner cases, so you'll have to basically decide what you want to do, right? So here, if all the coefficients are greater than TC, right, then if all the coefficients are greater than TC, then you have to, the thing we decide to do is we can't really merge, right? Because we can't, it's unlikely that this will be a good linear relation. So there's unlikely it will be a successful merge, right? So you have to somehow, right, make sure that, like, in that case, you do something where later on the merge doesn't get done. And similarly, if no coefficients are greater than TC, then also you can either not merge if the score is not very good, or if the score is good, then you have to basically bound the neuron by a constant thing, right? Because here, what does it mean? It means that the inputs, there are no inputs, right? So if there are no inputs, then like the zero linear combination is very good, which means that the bound is actually going to be, if there is a good bound, it's going to be just a constant bound, right? So these two corner cases you have to keep in mind while finally when you write the code, and I'll leave it up to you where you will put these corner cases, but it will be somewhere in step 2 itself. But where within between algorithm 1, 2, and 3, that's going to be up to you. I think, I feel like maybe corner case 1 should go into algorithm 1 and then corner case 2 in algorithm 3. But again, that is going to be up to you. That's going to depend on the exact structure of the code, I think.
Yeah, but both of these things will require, of course, for a particular TC, this will require you to look at the coefficients and compare it to TC. So,
right. Another way is that you're getting this list, right? You're getting the list of neurons with large coefficients. You can also see whether the list has, like at the end of this loop, you can check whether the list has nothing in it or does the list have everything in it at this point, essentially.
Yeah, so that's why in your initial experiments, this is something that we discussed with the other team, and we should probably point those points out. Listing some of the things that we have to list.
Right, I'll actually maybe create I'll make a note of this for the benefit. Yeah, so in the initial experiments, these are some of the outputs that we want. So of course, the outputs that we have already mentioned is histogram, right? And if you find that the histogram is something like just a single bar and then nothing, not much, right? Then do zoom it. So the histogram should be appropriately zoomed.
Yeah, Diganta had asked you to initially split that range, the min score and max score into 20 intervals. Okay?
Right.
Yeah.
So we are already seeing that for most of the thing that it is all bunched.
Right.
Beginning.
So
just
yeah. So what ends up happening is the histogram ends up looking like this basically, and then most of these are really small. Okay. So we're not really then interested at all in this. All the information we're looking for is actually being condensed in this one bar. So what we would like to do then is just to zoom into this bit, like create a histogram where the intervals are maybe 20 or 30 divisions of just this small range itself, right? So what I mean by appropriately zoomed makes sense to you, right?
you're refining that sub-interval into even smaller intervals.
Is that okay, Soham?
Yeah.
Yeah. Because this is one thing. The other thing is, if for some of the lower coefficients of the low S-score neurons, print the coefficients. This will give an idea of what the best linear fit expression looks like, right? And also keep track of how many instances of corner 1 and 2 you're seeing. So just for the initial experiments, you don't need to actually write any code to handle CC1 and 2, because when we say handle, we mean do something about the merge or not do something about the merge, right? But for the first experiment, you don't need to have the merging code in place in any capacity. But at least keep track of how many neurons are there where you're seeing everything is greater than TC, or everything is less than TC, right? Or at least what you can do is you can keep track of how many instances of, instead of let's say CC1 and CC2, how many instances of this situation we are seeing where every coefficient is 0. Right? So this is basically sort of CC2, but CC2 doesn't say 0, it says less than TC. So it's kind of similar to TC2. Right? But basically keep track of how many instances you're seeing where every coefficient is 0, or very close to 0, like 10 to the minus 13 or something like that. Right? So these are the few things. I'm not missing anything, right, sir?
Now, one point that you want to stress is that in collecting this information, they'll have to consider only ReLU outputs. The nodes, and not the thing which you said earlier. You explained.
Yeah, I'll write it down.
So just so when they output, let them not include. They may include only neurons that are outputs of ReLU.
Yeah, because otherwise if your neuron doesn't have a ReLU node and you take its output, then what you'll be getting is you'll be getting an artificially low score because you already have a linear best fit function, right?
But I don't know,
which is the layer itself.
Is the DNN format that is used, does it distinguish between the linear output and the ReLU output? Does it give two distinct node identities for those two?
So when you say format, you mean our data structure? The data structure we decided?
I don't know what data structure for the DNN that is being used by their implementation. Okay, so that's why.
So you're basically referring to our data structure itself, right?
So in your data structure, if it is different, then
there is a distinction. So there is this table which will keep track of type of node, For example,
and this is relevant. Okay.
Yeah. So here you can sort of add.
So Soham, will you be responsible for actually generating the output and reporting it?
As in, sorry.
No. Who is the person who will actually be running? Once Dhruv gives the data for particular, he generates the data for various models, correct? So who's the person responsible for running and producing these 3 outputs? Histogram.
Yeah, I think I am.
So that's what I asked. So which means then you will have to keep this in mind. Yeah. Okay. So with some implementation, assuming that Dhruv gives his thing by tonight, you can do all the preparatory work, with some of which you've already done. And so I'm hoping that we can expect your initial experiments by tomorrow, correct?
Yeah, hopefully.
Yeah. Okay. So once again, if you have any issues, communicate that.
Yeah.
To Digata, you also include me in the CC.
Yeah. You can write to us basically. Sorry. So you're saying something. So I'm sorry. Hello.
Yeah.
You're saying something?
No.
Okay. Sorry. Yeah. So right. So then I think we can ask.
I think so. I think you have any other questions with regard to completing not just the initial experiments, but finishing up coding of algorithm 2 and 3, which includes identifying the merge group and its input neurons and considering corner case 1 and 2.
Right.
So as of now, I'm assuming you understand.
Right. So basically, essentially, step 2 is okay. Is that the case?
Yeah, that involves completing coding up algorithm 2 and 3.
Yeah, it should be okay.
Yeah, sure. So you don't have any immediate doubts, essentially.
Not immediate.
Yeah, sure. So I think we'll move on, right, sir?
Yes, please.
Yeah. So Shodim, what's your situation? How are you getting along with step 3?
I think I'm understanding everything I need to do. I'll use CP to solve the LP as the LP solver, and then use Marble to shift the plane up and down and get the correct mode.
Right.
Algorithm 4 and 5, I don't have any problem, and algorithm 6 is just implementation of algorithm 5. The main issue with me right now is I installed Ubuntu dual boot, so I'm installing Marble again.
Okay.
Worst case scenario, I can use the Marble I installed on WSL, but to make it more swift, I'm installing it again.
Right. So WSL didn't work out at the end for you?
Not particularly, but I think I'll get it on Ubuntu.
Yeah, you could have. Actually, yeah. I don't have any experience to speak on whether it should work or not. But yeah, I think long-term installing Ubuntu seems to be the best way to go about it. But yeah, having to install an OS is. Yeah, but if you had come earlier, we could have probably fixed this installation issues. But yeah, okay, sure. So once you install Ubuntu, you'll be done. But have you written the
I have
LP
installed Ubuntu and everything. I'm installing Marble right now. I've set up everything, Jupyter Notebook.
Right. So
I'm just installing Marble.
Right, but in terms of the code, then do you have any code already written? Because
not right now. I'm writing it.
Yeah, sure.
I don't have any problem with the pseudocode. I think I understand everything.
Sure.
Yeah, but you should get started, okay? Because
I'm installing Marble, then I'll
start coding.
Algorithm 5 requires Marble, so I haven't done that yet.
Yeah, that's thing now. So you could still write the code. Yeah. That's fine. But there is also one task which has not been listed here, which I guess since Akhoury is the one that I would suggest that he should do it, or even once task 1 will be done by today, maybe Dhruv can contribute towards that too. That is to choose some 3 modules that you will actually be eventually doing that that overall verification test on, that loop that Diganta wrote. And I want those 3 networks, the DNA modules, to be different. I mean, team 1 to use one set of, pick one set of modules and you another. And then for each of those modules, you pick one safety, 2 or 3 safety properties and the robustness version of it. Okay.
Right. So I think
the safety version, it's already there. Apparently, Diganta, you should point out the link to the properties, the robustness version of the property, so that you should be looking at picking those properties and then be ready with for you to test it. Yeah.
Right. So basically, there should be 4 total model and property pairs. Is that okay, sir?
Yeah.
I'm just writing this down because I think we didn't write it down in the last meeting with the other team, right?
You didn't write it down, but we did mention it.
Yeah, we did mention it. Yeah,
but I had another task for a part of that overall experiments.
Yeah. So this is the long-term experiment, not the immediate experiments, right?
Yes, yes. But I wanted it to be part of the proposal, so that is missing from their proposal. Yeah.
So then when you say model and property pairs, you'll have to basically choose 2 safety properties. And when I say this safety property, what I mean is something from the paper that you have.
Yeah, that's right. And then choosing the thing, and I guess there is some, once they implement it, that module will have to be fed in and then converted into an abstracted form for which they'll use their code, correct?
So that is so when you're saying reading the model,
that they will do as part of actually conducting experiments. But I think doing the preparatory groundwork for choosing the modules. Okay.
Right. But I think just feeding the model into the code, if I'm not understanding it wrong, it's all that code is already there with Dhruv. That's just reading the ONNX files, right?
Yeah. So then he could probably run
it. But choosing the model is
then he can keep it ready, no?
Right.
So that, for each of the properties, when he generates the data, he has to generate it in such a way, keeping in mind what the input constraints are. All that will require some time. So what I'm saying is, once the choice is made, Dhruv can actually, as part of his effort to generate the sample data, he could keep ready the sample data for those things, for those particular properties. No?
So I think what we can what my suggestion would be is make sure with Dhruv that when you write your sample data generation and your this code as well, like the interval propagation code as well, make all of that in some sense be parameterized by these initial input intervals. So make sure that the input intervals that you have, those are you can sort of very easily change them, right? So that if you're trying a different property, then you just need to change something at the top of the file. Or even better, if you could somehow take it as an input from an external file, but if that's too much work, at least make it parameterized. So is that okay?
Okay. Yeah. And one thing. Okay. Yeah.
Go on.
You were saying something. I was going to say something irrelevant.
No, I was just going to write down and the fact that you also need to you have to choose 4 properties, so 2 safety properties and the robustness version of the safety property. So I'll just write that now. That's all I was going to.
Okay. And one thing, I was checking out the properties for the various DNNs.
Yeah.
So, in what order do we have our 5 inputs? Currently, I'm having them as first rho, then theta, then psi, then v on and v int. So
no. So remember, the order is going to be fixed in the network itself, right? Like you have to make sure that the network. So basically, when they trained the network, they trained it where the data was in a particular order, right?
Right.
And that you have to always everywhere consistently maintain that order, because otherwise what you're doing is essentially mixing and matching input variables, right?
Right. So in which order do I like arrange the
Right. So if you go
input?
and look at the paper, I'll just bring it up, I think.
Yeah.
Yeah.
Because I just tried out an input and I'm not getting the correct output.
Yeah, the order is also important, and then there is some scaling thing that you guys realized early on, no? So that is also required.
Yeah. Just a second. I'll just bring up the paper.
Right.
Yeah. So if you look here at this appendix 6, they give this order, right? Wait a second. Where is it? So okay, not in appendices. There's things a little bit before there is a section where they describe.
Okay.
Wait, just a sec. In section 6. Yeah. See, this is the order. First is rho, then second is theta, then third is phi, then v on and v int.
Okay, so that's weird.
Why?
Because like when I'm running the inputs in this order only on the original DNN, I'm not getting the right output.
Yeah, but that may be because of scaling. Okay, there is a scaling that you have to adjust. No, Diganta, you remember that?
Yeah. There is a scaling issue, and I think that was like you guys found the particular scaling file within the VNN lib. Like that was figured out, right? I think I'll.
Yeah,
so
VNN complete has the scaling.
Very early in the class itself. Okay, so maybe you can make it clear, because I don't know if everybody was paying attention or present in that class. Actually, you guys brought it up.
Yeah. So Soham, I think you were the one who figured out the correct scaling, right? If I'm not wrong.
Yeah. I have this. I mean, for the network I was using, I have the scaling. It is there in the VNN complete file.
Yeah, and that is the same for all the networks, right?
That I have to check. I
think it will be the same for all the networks.
It should be. I mean, but I don't know.
But yeah.
Okay.
So anyway, share that scaling with Dhruv as well.
Yeah, sure.
So when I create my 2000 length input, so I'll have to incorporate the scaling there as well.
Yeah. So basically, what the scaling means is that see the properties will specify theta in radians, for example, right?
Okay.
But then the scaling is going to scale. So the radian means it's in like the ranges between minus pi to pi, right?
Right.
So for example, if you look at this property 4, the input constraints are these, right?
Right.
So if you look at rho, it's between 1500 and 1800, but then there'll be some scaling which will convert this to some other actual values, right?
Okay.
So then rho will be something else over here.
Then normalize it to something. Huh? So
Yeah. So for example, the scaling might be, let's say, divide by 1000, subtract 500. Then rho will be 0 to minus 0.3. Oh, sorry.
I see.
0 to 0.3, not minus 0.3. Yeah. You get the idea, right?
Right.
Yeah. So then the idea is that in the network, instead of like, you'll assume that the network doesn't take actually the input and feed, but in some other scaled unit, essentially. Scaled and shifted and all.
Okay.
Yeah.
So I'll try that out.
Right. So I think this is it. Do we have anything else?
Yeah, any other questions for now? I mean, you can always ping us by email.
Right. And you guys would like this file, I'm assuming. I'll just share it in by email.
Yeah, I will, upload this the recording of this lecture also. Okay,
Right.
so you share that on Moodle.
I'll share it on Moodle location.
Okay. Yeah, hopefully you will make some progress by tomorrow, and then we can get.
Yeah. So, are there any doubts? If not, I think we can